Hello, Honors Chemistry, and welcome to Chapter 4, which, just like we said for Chapter 3, should be largely review, again, from 8th grade physical science. I know if you were at St. Mary's with Miss Carol, you did a whole quarter on the principles of chemistry. And even if you weren't here, right, I am sure that somewhere between 7th and 8th grade, you did a whole year on physical science, which would have included an introduction to chemistry. Really, Chapter 4 is an introduction to atoms, which is the foundation of all things, not just chemistry, but anyway. So one of the critical foundational things about atomic theory is Dalton's atomic theory, right? So obviously, like your book goes into, the concept of an atom has a long history, right? But it isn't until Dalton that there is enough technology, and this is technology for the time, where you could propose a theory, right? Something that, when tested, seems to be true over and over again, okay? So anyway, his theory states that each element, right, so that is every individual element, so for example, all of iron or all of sodium, etc., is composed of tiny indestructible particles called atoms. Is that true as written? No, right? They are not indestructible, right? In that, hypothetically, just on a simple level, right, we can take out parts of it, like electrons, right? We know that there are subatomic particles, like the protons and the neutrons and the electrons, and those can be broken down even further. And so the concept of indestructible is not really true, right? Not to mention there is the whole nuclear energy and nuclear bombs, right? All of which basically tear apart atoms. So the concept of indestructible, not quite true, but they are tiny, right? And they are particles. And when we think about it, right, going back to what the definition of an atom is, being the smallest unit that retains all of the properties, right? Once we start to destroy an atom, it no longer has the properties of the element from which it came, right? So are atoms indestructible? No. But once we destroy them, do they still represent that same element anymore? Also no. So there is some ambiguity there. Okay, next statement. All atoms of a given element, right, so all atoms of iron, all atoms of lead, etc., have the same mass and other properties that distinguish them from the atoms of all other elements. Is that true as written? No, right? Because there are things like isotopes, right? Wherein isotopes have different numbers of neutrons, therefore they have different masses, but outside of having slightly different masses, all isotopes of an element have the same properties, right? So do they all have the same mass? No. But are their properties essentially the same? Yes. Okay. Finally, we get to principle number 3, which states that atoms combine in simple whole number ratios to form compounds. Is that true? Absolutely, because we can't have half of an atom. If we did, it wouldn't represent that element. It wouldn't have all the properties, right? It doesn't make sense. All right, evolution of the atomic model, right? So this is a slide stolen from this guy from this place. And basically, it just sort of highlights what your book talks about, right? Where with Dalton, the idea was that atoms were little spheres, right? Hard, indestructible spheres, okay? Thomson, which your book gives brief mention to, comes up with the idea through his cathode ray tube experiments, right, which were hugely important because cathode ray tubes then became the technology that led to the first televisions and, and that was the primary viewing mechanism for decades and decades, right? But anyway, cathode ray tubes, which discovered that there were little negative particles inside of everything, right? Little negative particles inside of everything. Which was the first clue that perhaps an atom is not an indestructible sphere, and there is something else happening on the inside of an atom. Rutherford, that gold foil experiment, which is in your guys' textbook, and there are simulations you can look at online, where basically, while it doesn't sound extraordinary, right, the conclusion took years to come to, right, but there was, like, I think your book says it's like 1 out of every, 22,000 or something like that, of the alpha particles bounced back, right? So when they shot the alpha particles at the gold foil, 1 out of every several thousand would consistently bounce back, which is weird because an alpha particle is so ginormous compared to what it was running into, right? which was hypothetically teeny tiny electrons, which have almost no mass, right? And the same concept applies, right? If a really big thing runs into a small thing, right, it should not be deflected very much, yes? Which is why the result was so weird, right? These giant alpha particles came bouncing back, which means that whatever they hit, right, must have been substantial enough to make it bounce back, right? And so it took several years, like I said, for them to come up with an idea that seemed to match that observation, okay? Bohr came up with the Bohr model of the atom, which I know you guys have experienced doodling in both middle school and ninth grade, where the concept is that electrons exist in energy shells or energy rings, right, that rotate around the atom, right, also known as the planetary model of the atom. But the problem there is it lacks the three-dimensional nature, and it lacks the differentiation for multi-electron species, right? As in the Bohr model was only accurate at predicting energy changes in single electron species, right? And so then Schrodinger came along, came up with the Schrodinger wave equation, which, should you have the honor of being a chemistry major, you will spend an entire year or two studying the Schrodinger wave equation. Oh my gosh, what a joy. But basically, to understand where we come up with the current quantum theory, the quantum model of the atom, okay? Which we will talk more about when we get to chapters 9 and 10, but for now we're just, talking very vaguely. All right. We all know that atoms are composed of protons, electrons, and neutrons. Things to note here, right? We have this column called AMU, right? Known as atomic mass units. And note that when we say atomic mass unit, right, you should in your head automatically understand that that means a mass, right? Approximately, right, 10 to the negative 27th kilograms in terms of mass, right? Which, if we look here, right, that seems to be what we understand an AMU to be, okay? So that when we talk about, for example, carbon-12, right, has a mass of approximately 12 AMU, right? And that has meaning, right? That ties back to this number of kilograms, right? So just bear that in mind, right? And note that for protons and neutrons, it is strikingly close to 1, but not exactly 1, yes? Close to 1, but not exactly 1. And obviously the charges, we should be comfortable with those, yeah? And obviously the mass of an electron compared to the mass of a proton and neutron is almost negligible, right? Almost negligible. All right, so then that brings us to our fantastic, wonderful periodic table. So groups you should know, right? Oh, by the way, these are our groups, yes, the numbers at the top. Our columns make up our groups or our families, as you might have referred to them previously. There are two numbering systems, right? There are the A's and the B's, and then there is just the sequential 1 through 18. Just note that whichever one you want to use, it needs to be consistent, right? So 1 or 1A, both would describe everything in this column, right? But when we get over here, for example, right, it would have to be 8A or 18. If you just gave me 8, that would be wrong for this column. Yes, does that make sense, right? And then obviously we have our period numbers, right, which are our rows, and which help us to identify where elements sit on the periodic table, right? Which is important because in a period, properties change in a predictable manner. In a group, everything in a group has very similar properties and behavior, right? And again, we'll expand on that when we talk about atomic structure in chapter 9. But for now, let's go ahead and identify some of the important groups that we should know about, right? So group 1, these are called these are our alkali metals. Group 2, these are our alkaline earth metals, right? And then we have all of these would be known as our transition metals, right? We have our everything that touches the stair-step line with random exceptions, right? So everything that touches the stair-step line, excluding aluminum and polonium, right, would be called our metalloids, right? So those things somewhere in between, right? And then going more broadly, right, everything here through here, right, So everything in beige would be known broadly as metals, right? Where all of this over here would be our nonmetals, right? And then some more specific ones, right? So this group here is known as the, right, noble gases. This group here is known as the halogens. What else? This is our lanthanides. This is our actinides. I think that's it. All right. Oh, main groups. And then obviously we also have our main groups, right? Where 1 and 2, 13 through 18 make up our main group elements. And so more often than not, when we talk about traits that are predictable, we are talking about main group elements, okay? All right, so then, like I said, when we get to chapter 9, we'll talk about what properties of an atom, right, in terms of its arrangement of electrons, sort of dictates where it sits on the periodic table and why the periodic table is so amazing. But until then, you just need to know these basics. All right. Thank you for listening. Be good. Stay tuned for the rest of chapter 4 in the next lecture. Have a great day. Bye.